Hello, welcome to another episode of All the Ideas. I'm Douglas Bebb, and this is Scott Little, one of the other Mad Fellows, and who's a PhD candidate in applied mathematics and computer science.
Hello.
Today we're going to be talking about some work that Scott has been doing and prepared for the SIAM General Conference 2013. I think we'll let him introduce what his topic was, and if you can, just kind of give us the brief description that you did at the conference, without benefit of the PowerPoint.
Okay, well, I wrote down some notes just so I could kind of have a outline to follow and be able to describe it, hopefully halfway succinctly and intelligently that makes sense to people. But why don't I start with the name of my topic, and this is also directly related to the research that I've been doing. And the name is Gelirken, Isoh Geometrics, and Transformation Optics to describe meta-solenoid electromagnetic singularities. Now, what this research is, this is a continuation of the invisibility cloaking research that I presented at the SIAM Partial Differential Equation Conference in November of 2011. Now, what I'd like to do, if that's okay with you, Doug, is kind of split this up. So I know it's a bit wordy.
Yeah, I think it's a little brain busting on the title at first. So I think breaking it up's good.
Okay. Well, why don't I start with what I'm going to do is kind of chunk this out into different categories, starting with the beginning of the title, which is Ritz-Gelirken. What Ritz-Gelirken is a methodology used to solve partial differential equations using a method known as the finite element method, which is used to approximate difficult differential equations, particularly partial ones. It uses a methodology called a weighted method that takes a variational approach and converts a basic equation into what's called a weak formulation, which is using a technique called integration by parts. If you guys have taken any integral calculus, you know what that is. And what it does is it takes the equation and converts it into a series of basic elements to create a grid. Anyone who's done CAD drawings would know how you produce a mesh and you contain something within a grid. Well, what the Ritz-Gelirken method does is it takes this equation, breaks it down into little pieces called elements, and then uses those elements to solve the equation in a graphic representation of that equation. It could be a fairly complicated method depending on the type of equation you're using, and how discrete and how detailed you want to get. There's what they call rough approximations, which aren't nearly as detailed, and you have less points on the grid, or they call them nodes, and they're farther apart. Well, the smaller that you make those nodes and the closer together they get, and the more detail they get, obviously, the more complicated it is. So that's kind of the starting point for solving this equation. And let me know if you need to break in or anything, Doug. Now, what Isoh Geometrics is, which is the second title in the title of my topic, it is a methodology developed by Dr. Hughes and his team at the University of Texas, Austin, to take finite element methods and combine them with CAD, computer-aided design. This was an effort to be able to utilize finite elements within a CAD environment at a one-to-one mapping. What that means is you're taking an element and it has an exact representation of that element within finite elements within the CAD drawing.
I know we've actually used these methods in some of our 3D design and testing verification of a work in the design process.
Yes.
So it's probably most engineers out there are going to be familiar with it.
Yes. And by doing so, what you're doing is you're taking what's called a NURB, which is a non-uniform rational B-spline curve, and that's defining the mesh within the finite element. So you're taking this curve that is a CAD drawing, a piece of a CAD drawing, and it's using to define and create the actual element with finite elements analysis. So it's an interesting correspondence that Dr. Hughes and his team developed, and it really kind of adds that extra dimension to the ability to solve some of these more complicated equations. So moving on to the next aspect of the title, which is transformation optics. Now, what transformation optics was developed by two physicists, Leonhardt and Philbin, at the University of St. Andrews in Scotland. And what transformation optics is an effort to use the equations of general relativity to define the curvatures in electromagnetic or acoustics mediums. So in other words, you'd be using general relativity to define curvatures in space-time, when you have a large gravitational object such as a black hole. Well, what you're doing is you're basically using those same equations to define the curvatures in electromagnetic medium, like an electromagnetic wave, a light wave, a radio wave, or an acoustical wave, a sound wave. And it's describing these extreme curvatures that you would normally see around an extremely massive object, again, like a black hole or a very large star. And they've been able to utilize this to come up with some pretty interesting results. A big part of what their research involves is what's known as a metamaterial, which we've been working on for some time here at Mad Fellows.
I think probably for the better part of 3 years we've had our hands in that research.
Yeah.
We've been working on different aspects of it, from practical application through, which ultimately led to some of the inspiration behind this work.
Yeah, there's always the kind of cooperation between the applied and the theoretical in our work. We always seem to kind of feed off of each other when it comes to that sort of thing. And in the case of the metamaterials, what a metamaterial is, it's a material that creates a repeating pattern of some sort of metallic substance, usually copper, that forms what's known as a negative refractive index. And what that means is light or some other type of electromagnetic or acoustic wave is coming into contact with it, and it's reversing the refractive index on that particular incident wave. So basically turning it around 180 degrees. And the significance of that is not only being able to bend light and other types of waves, but also creating things called perfect lensing, for example, where you can have a lens with almost no interference to use in objects such as telescopes or microscopes. Also wireless devices, which we've experimented with at Mad Fellows.
Viewing objects below the diffraction level.
And of course in cloaking. This is the main device that they utilize to in cloaking and visibility cloaking research, where they'll form a concentric circle made of material and put the object within the center of those circles, and they can bend. I think they're to the point now where they're actually being able to bend visible light around that object, and you can't actually see it. So it's an exciting field of research that has many different applications. For example, solar cells. That's another example of an application that you can use for metamaterials. So in this case, what we're representing is what's known as a metasolenoid. A metasolenoid is a solenoid that is made of metamaterials, basically, in its simple form. And what that refers to, a solenoid, is something that converts electrical energy into mechanical energy. Well, this is a solenoid that's using the concept of negative refraction to produce some sort of mechanical work or something mechanical energy-wise that could be utilized for a variety of reasons. And the reason that we wanted to use a metasolenoid for this research is that they've already produced different types of perfect refraction behaviors, such as creating singularities. It's very similar to singularity for gravitational black hole, where you're condensing down the force into one single point. Basically, it has only one dimension, and that's the purpose of creating an electromagnetic singularity, is you're condensing that wave down into a single one-dimensional point. Now, what this what the main focus of this research, as far as the wave equation, is what's known as a Helmholtz equation. And the reason why I chose to focus on the Helmholtz equation, it's a very versatile equation to use with electromagnetic and acoustic waves, and it's directly related to the Maxwell equations for electromagnetism and other types of waves. So the Helmholtz equation is a good choice to use when you're dealing with types of moving electromagnetic waves. So that's the representation of the wave equation in this research. And now you may ask, well, how does this all tie in with other, I mentioned gravitational black holes. Well, one of the motivations behind this is there's been some research done on creating electromagnetic black holes using metamaterials in a laboratory. And this is part of the research that we're beginning to conduct at Madfellows, correct? That we're starting to develop devices that we are going to test to see if they can create an electromagnetic singularity. And
I think also some of the things that we've been looking at are some of the limitations and problems for engineering a physical metasolenoid that creates these effects. That's been the biggest challenge, is engineering around those issues.
Right.
And that's something that we're going to be able to hopefully soon be able to experimentally verify some designs.
Yes, we've seen, looking at some of the other research, we need to get verification that some of the research has been producing these electromagnetic black hole singularities in the lab. We need to verify that they're actually producing the results that is being claimed in the research. Well, the theory behind all this is the fact that you can't create an at least at this point with the present technology, and probably not for quite a while, being able to create a gravitational black hole anywhere. It would be way too massive, obviously pretty dangerous at the same time. So a good safe analogy to the gravitational black hole using the equations of transformation optics is to create an electromagnetic black hole in the lab. Now, in addition to just the equations of general relativity, this brings in another aspect of my research, which is string theory. This string theory, just a kind of very brief history of overview of what string theory is an effort by physicists to combine general relativity and quantum mechanics in an area called, very, 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 very small length called the Planck length, which is theoretically, and of course, since they haven't been able to test this, the energies are way too high, but the Planck length is approximately 10 to the negative 35 meters, which would be far beyond the energy that they have in the present particle accelerators to be able to measure something at that length in a laboratory. So, another aspect of string theory is there's two basic types of strings. There's open strings and closed strings. The open ones refer to a string that looks like a piece of string. A closed one would be analogous to a rubber band. And the types of strings relate to the types of elementary particles. There's bosonic strings, which refer to bosons, which are photons, and other bosonic commutative particles in quantum mechanics. Then there's the fermionic strings, which are like the electrons and the quarks. And in the basic, a string is supposed to represent the basic unit of energy. Now, what they do is they vibrate at a certain frequency, and you can describe them using what's known as a harmonic oscillator. If anyone's familiar with, oscillation and fast Fourier transforms and things like that. So that's just kind of I just wanted to kind of introduce string theory as a little bit and give it kind of a very brief background. And strings represent movements in multiple dimensions that are compacted within the movement of the string at a very, very small, it's very, very small size. And that's why we're not able to see what they refer to as these extra dimensions. An analogy would be a garden hose. You look at a garden hose from a distance, it looks like a line, one-dimensional line. You get closer, it gains another dimension of width. You get closer still, you notice that it's actually a series of circles in a row, and that you get another dimension. And you were to break that up even further, you can see little bumps and ridges in the garden hose. It gets even more so. So that's just kind of an analogy to help understand how these extra dimensions are actually there, because they're needed to represent the basic elementary particles and forces going on. So that being said, strings are said to move in these what are known as branes. A brane is basically a manifold, a sheet, a multidimensional sheet in space-time, described by general relativity equations, i.e. transformation optical equations. And a black hole is basically a series of branes that have been kind of compressed and wrapped together, like you would take a tube of construction paper and make a funnel out of it. Due to the very strong gravitational forces, creates kind of like this long tube of these different, this piece of paper kind of wrapped together. That's kind of an analogy of what a brane is. A black hole producing a series of wrapped together branes. So, how does that tie into string theory? Well, an open string needs to be attached to something. So it's not just moving. It can't, it needs to have a boundary. As if everything that you do in physics, there's always boundaries. And the ends of the open strings are connected to what's known as a D-brane. A D-brane is, the D in D-brane refers to Dirichlet, which if anyone familiar with solving differential equations, a Dirichlet, a boundary condition is a fixed boundary. So the open string is connected to that D-brane, and it has a fixed boundary, so that it's moving, only where that brane is going to allow it to move to. Okay, now how does that all tie into what we're trying to do with electromagnetic black hole singularities? Well, there was a series of researchers in China, led by Li, that had attempted to create electromagnetic black hole singularities in a lab, and using them to test some of these string theory ideas that we're having. Now, where I took my research and based it on what they had already done with Li, and tying in the Isoh Geometrics and the transformation optics, and kind of conglomerating all this into be able to produce electromagnetic black holes and test string theory and other things.
So you're really trying to produce the next step in
Right.
terms of this research.
Yes. And I think, as far as I know, this is kind of groundbreaking in a sense that I don't know of anyone that's using Isoh Geometrics and transformation optics to test electromagnetic black hole singularities. It could be wrong, but I've looked through the research and I couldn't find anybody else that's actually doing this at this time.
Also, the last time I checked, I'm not aware of any other verification of the Chinese team's research. So it'll be interesting to see if other people pick up their work.
Right.
And that's going to be one of our first steps, too, is to actually going to be trying to duplicate their research.
Right.
To see if we get the same results that they were looking at before we proceed forward.
Right. Yeah. Yeah, that's always a good starting point, especially on the applied side, to verify that we're getting the same results that the Chinese team was. And on the mathematical theoretical side, I'm using what's known as the Born-Infeld action. Every string has a movement, and that movement is defined by an equation that's known as an action. It's like a point has a certain Schrodinger equation, elementary particle. That's a less dimensional action of that particular particle. Well, the Born-Infeld action describes the movement of the string on a brain, but it also includes the electromagnetic force of that movement. So what you're doing is you're taking the movement of a string on a brain where it's attached to that brain, but it also has an electromagnetic force to it, which ties directly into electromagnetic black holes. What I had done is I'd modified the Born-Infeld action to include the Helmholtz equation that I'd already solved within the Isoh Geometrics and produced the curvature using transformation optics, and inserted this what's known as a virtual Helmholtz equation, which is a Helmholtz equation in virtual space, which when you get into bending electromagnetic waves, just like space-time, you work in virtual coordinates. Excuse me. So that's how I was able to kind of tie all this together. And it turns out the Born-Infeld action also includes the Maxwell equation. The force of the Maxwell equation is also included within that string action. So we're kind of, by conglomerating all these things, we're kind of tying all that together. Using the Isoh Geometrics to solve the equation and produce it realistically in a simulation, using the transformation optics to create the curvatures and also producing the simulations, using the string theory aspects of it to describe, and also the electromagnetic meta-solenoid aspects to describe the singularities, black holes, and the string theory, and verifying everything by experiment, doing the applied side, and actually getting to the point where we can build a meta-solenoid device that will produce electromagnetic singularities in the lab and test that and verify that. So kind of going from A to Z and tying all this together.
Okay. So I think that's a pretty good synopsis of what you're working on, and what we're trying to work on collectively at Madfellows. I guess just one other question I would want to ask about the SIAM conference. Certainly we were both there at the conference. Was there anything that stood out to you or was particularly inspirational there that you really took away from that event?
Well, it's just, I think it's it's the situation where you realize, sometimes we all work in isolation, depending whether it's academic, industrial, but to see such a large concentration of applied mathematicians in one area is just phenomenal. And to realize that there's people working on similar things to what we're doing. They may be in an academic setting, but their work is very similar. I mean, I can read people's papers, but it's not the same as actively listening to somebody talk about their research or actually talking to someone personally about their research and realizing, hey.
Well, you certainly don't get that excitement out of them through a paper. So
exactly. And I think that if it's anything that anyone is able to attend who has these either aspirations or is, a theoretician, applied mathematician, or an engineer or whatnot, has the opportunity to attend, they should. You'll walk away getting something out of it, no matter what level that is.
Well, I think that's great. I think that's probably it for the show. This has been another episode of All the Ideas. I'm Doug Webb, and this was Scott Little. Thanks for joining us.
Thank you. I appreciate it.